Start today with our keynote speaker, Marc Lipsitch from University of Harvard School of Public Health. So Marc Lipsitch is epidemiologist and professor of epidemiology at Harvard School of Public Health, and he is the director of the Center of Communicable Disease Dynamics. So please, Marc, you can start.
Thank you. Can everyone hear me okay?
Yes.
Great.
Yes.
All right. Thank you. And I'm really sorry not to be there in person. As I was just telling people, I teach both yesterday afternoon and Wednesday afternoon and couldn't fit the trip in between. But it looks like a great meeting and it's a privilege to be a part of it. I'm pleased to provide some perspective on what I think some lessons of the pandemic have been about surveillance. And I will say, I think I have a very US centered perspective because of where I am and the fact that I'm now, although I'm speaking in my personal capacity, I'm also now working with the CDC on a part-time detail to set up a new Center for Forecasting and Outbreak Analytics. And so I've been very focused on the US perspective. I think many of these issues are about systems and how they work. And so I think that the details may differ, but I look forward in the discussion to thinking about how Canada and other health systems compare and contrast with what I'm going to say. I'm also going to speak a little bit about work that I did with Israel. So with that preface, one thing that I've really learned from the last few years is that everybody thinks they know what surveillance is, and they have very strong opinions, but they're not all the same strong opinion. So it's a lot of different and strongly held views. And I think that's because people come at it from such different directions. One of the most interesting perspectives on surveillance I've ever read is this pamphlet from the WHO, which I don't think has been very widely circulated, but it's about the ethical issues in public health surveillance. And when I picked it up, I thought it was going to be about privacy and what you shouldn't do and the need to make sure that people aren't treated poorly by surveillance systems and so forth. And there's a little bit about that, but really it's actually quite the opposite in terms of its overall message. And what it argues, and I think this really is the basis for why we all do what we do in trying to improve surveillance, it argues that surveillance is an ethical imperative for the simple reason that if people's health conditions are not known to their government, then the government can't and won't do anything about those health conditions. And that therefore governments have an ability to ensure high quality data collection and processing, and the global community has an obligation to support one another to try to make that possible in places that have less resources. So I think this is a very compelling vision, of course, with the caveats of privacy and appropriate safeguards, but I think it's a rather inspiring starting point. Other perspectives that I have encountered in recent years are the kind of data science view of surveillance that, in some sense, data are there, and the goal of improving our surveillance systems is to improve the ability to use those data. And this is one acronym that's been widely used to describe some of the important aspects of good data. But this view focuses in a way on the plumbing, on the pipes, the data pipes that get the data from wherever they start to authorities who can interpret them, maybe to academics who can reinterpret them, to other sources of insight. And the point here is that the plumbing has to be sound. It has to provide get the data places quickly and in a findable way, and in a way that that can be reused and so forth. This is also very important, but again, incomplete in the sense that the content is less emphasized in this view than the sort of process. We've heard a lot in recent years about genomic surveillance and wastewater surveillance and other laboratory-based types of surveillance. And I think one of the issues that has made it challenging in public health to interpret laboratory based surveillance is that laboratories are not usually in the business of doing surveillance as their primary goal. Some of them are, but more often they're there for interpreting clinical specimens, which may be specifically focused on difficult or unusual clinical specimens, or they're there for research, which is by nature focused on what's novel and interesting rather than what's typical in many cases. So it's very often the case that laboratories, for very good reasons, enrich their samples for what's unusual and interesting, and maybe are looking for some unusual marker, perhaps an S gene target failure or a non-S gene target failure in the case of COVID, and they will enrich their samples to overrepresent those interesting ones. And that has the consequence that the samples that we get out when we use those for surveillance may be unrepresentative of what's present in the source population. It was nice to see Mauricio sitting there because just before the pandemic, he and I wrote a short piece in a very obscure journal, but it is findable on PubMed. And that piece tries to make the case that surveillance should be designed around decision-making, and it should be designed to support with evidence the sorts of decisions in a pandemic that public health authorities have to make. And I don't know how well you can read the small print here, but some of those decisions are things like the overall scale of the response, who should be targeted for measures of direct protection, for measures to reduce transmission, how we should balance those kinds of measures, when we should scale up and scale down responses, and so forth. And to answer those, we need certain kinds of evidence about transmissibility and severity, who is at greatest risk, and so forth. That's the line of evidence here. And then the surveillance inputs are the sort of basic numbers that go into trying to make estimates of those quantities. And we use statistical models and transmission dynamic models to try to integrate evidence from different types of surveillance systems to answer questions. And the goal here is that the notion here is that we should set up these surveillance systems in order to feed those decisions. And in my role at the US CDC, working to set up the Center for Forecasting and Outbreak Analytics, that's really sort of our view, is that our job is to provide these analytics to support decision-making, and therefore we have a strong interest in trying to enhance surveillance that will provide the kinds of inputs that we need. In most countries, and I know this is true for the United States, I think this is largely true for Canada. Please correct me if I'm mistaken. The primary means of estimating how much COVID-19 was around was case counting, supplemented with hospitalization counting and death counting. And if we compare that against what epidemiologists typically want to know, which is incidence and prevalence of disease or infection, we can see that there are lots of filters and barriers between the basic epidemiologic quantities and the numbers that we can observe. So some of those barriers are reasons to test or not to test, due to attitudes or fear of losing work, depending on one's employment arrangements. If people want to test, there may be shortages as there were at the beginning. It may be difficult to find a test. And then if they get the test, the type of test, of course, determines whether it accurately reflects their status and whether the test gets reported at all. And so there's a lot of interference between these basic epidemiologic quantities on the top and the observed quantity at the bottom. And those numbers are those barriers and determinants are changing in space and time, which to me has been the single reason. This slide is really the reason why estimating the issue, the effect of new variants, of new intervention measures, and of other things has been so challenging throughout COVID-19 that we're not measuring the thing that we most want to understand. So with these different views of surveillance, I think there's an argument to be made, and this is what I believe, that we should really try to conceive of surveillance as a multiple blade tool, where we have a number of different instruments for surveillance that are each designed for specific purposes, and that we don't try to make a corkscrew work as a whittling blade, and we don't try to make a magnifying glass work as a can opener, which we often have had to do because of the paucity of data. And I think that the purposes of surveillance can be broadly defined in a pandemic as detecting new things entering one's territory. And new things could be new viruses, new variants of a known virus, or so forth. Assessing individuals and trying to figure out what kinds of treatments are needed. Characterizing severity of the infection and the effectiveness of countermeasures, and assessing the burden. I think if we could do those four things well, we would have really most of what we need to inform decisions. Obviously, there are some other pieces, but I think these are the biggest of them. And so I want to talk about a couple of those. We will not go through all four, but go through the first and third just as examples to sort of understand why and how we might approach those specific goals, while understanding that the systems we set up will be better tailored for those than for the other ones. So why do we want to detect new infectious agents? Well, I think that's quite clear to everyone, but just to make it explicit, one reason is because if something is of sufficient concern, we want to activate countermeasure development, and both the G7 and the Coalition for Epidemic Preparedness Innovation have proposed this notion of a 100-day mission to have vaccines, therapeutics, and diagnostic tests available within 100 days of detection of a pandemic threat. If we can detect it early, that means that in calendar time, we will be having the 100-day mission will be more effective than if we detect it late. COVID has alerted us to something new, which was really not on most people's radars, at least on the time frame of in which it's happened, which is the need to prepare for the spread of new variants, even within the same season or the same year as an old variant. Certainly in pandemic flu, we had that notion, but it was kind of a one-time thing, and then we dealt with the pandemic. We didn't deal with arguably multiple pandemics each time a new variant appears. How do we do that? Well, I think one clear lesson from COVID is that geographic scale matters for detection. COVID has done a number of things that it almost feel as if they were designed to educate us, or to tease us, or to make us scratch our heads. But one of the things that it's done to educate us is that four of the first four major variants that were detected on 4 different continents. And these are many people don't remember Gamma because although it looked really fearsome at the time, it did not spread as widely, but and sort of the same with beta, but nonetheless, the first 4 major variants were detected in 4 very different places. And so the need for global surveillance is, I think, very clear. The other aspect that's important is scale and size, and certainly bigger is better in terms of surveillance for new variants, because we can pick up more things if we and pick them up earlier if we scale up our system. But in a trade-off, for example, between geographic scale and size in any given place, I think it's important to remember that that there's this rule of 3, which is just a consequence of how the Poisson distribution works, that says that if you want to find something at a frequency of X%, you need 300 over X samples. So if you want to see it at 1%, you need 300 samples. If you want to see it at 0.1%, you need 3,000 samples. And that's not so many. I think 0.1% is a frequency that most people would say is probably even lower than what we need to see initially. We need to be certain of picking up. So I think when we're talking about surveillance efforts, broadening them and making them more representative is perhaps even more important than scale beyond a certain point. What about quantifying burden? I think there are, again, many reasons to want to know whether we have a lot of an infection around or a little. Some of those are just to understand the trends and have situational awareness, to understand how population immunity is evolving and whether most people have been infected or not. We're currently in China seeing people saying that that 80% of the population has been infected in the last little while, and many questions about whether that's reliable or not, but only by measuring infections can you have a reasonable estimate of that. We'd like to be able to evaluate control measures and see whether various attempts to slow transmission have actually done so. We want to understand hotspots and needs so that we can move resources to areas, say geographic areas that are most in need. And importantly, throughout COVID, we've seen dramatic inequities. And again, I'm showing US data here on the bottom right for the race ethnicity breakdowns of COVID cases. And you see initially higher numbers in Hispanic Americans, and then in American Indians and Alaska Natives. And the disparities are persistent, although as immunity has been acquired by certain populations, the patterns have changed a little bit. So how do we do that? I think for understanding burden, this is one function of surveillance where representativeness is exceptionally important, unlike almost all the other purposes, or at least some of the other purposes. So this is a data from Luxembourg, where the country decided very early in the pandemic, starting from early March, to start testing large proportions of its population, and it was actually testing on the order of 10% of its population per week. Small population, so that's a more manageable thing to do than for some other places, but really a remarkable effort. And they were therefore able to track the prevalence of infection by PCR over quite a long period and understand the trends in the data. Also important is data completeness, so that you understand who is being infected and can make some estimates of these kinds of inequities and other geographic and other patterns. Another approach to quantifying the burden, or at least the trend of the infection, is something that we developed over 2021 and published in this article on the right. And I mention this mostly because we are all struggling with incomplete surveillance pictures. And I think in the short run and the medium run, the success of surveillance in most countries is going to be due to combining different types of data and squeezing the most information possible out of the data that exist. And I think that the ability to use viral load data in cross sections of the population is really a different kind of data source, and it has different biases and different limitations than case counts. And so what the approach that we developed here does is it uses the fact that the viral load curve in people is asymmetric. So there's a fast up and a slow down, which you can see here at the right. And it uses one other important fact, which is that in a growing epidemic, most infections are new. That's just the nature of exponential growth. And in a declining epidemic, most individuals that you sample will have been infected for a longer time. That's the nature of exponential decline. It's sort of basic demographic theory transplanted into the age of viral infection. And so with those two facts of early infections being overrepresented and having higher viral loads when the epidemic is growing, you can use the shape of the viral load distribution to estimate the direction of change of the epidemic. So I think, we're now trying to apply this in different settings and see how we can expand it and what its strengths and limitations are. But I think it's an example of trying to find roughly orthogonal data sources that can give you pictures of what's going on, so that you're not reliant on the limitations of a single data set. I said in the short run, we have to cobble things together. I think that what we should all aspire to in the long run is to be able to take random samples of our population, or nearly random samples, and assess whether those individuals are infected and what they're infected with. And Natalie Dean made that case, I think, really compellingly in a short piece in Nature a little while ago. But even more compelling than her arguments, which are very good ones, is the experience of the UK, where they set up two such studies of nearly random samples of the population. One of them called REACT, which was serial cross sections, and another one called the COVID infection survey, which was longitudinal studies of households. And from those surveys, they were able to estimate prevalence of infection and therefore incidence, cumulative incidence, what variants were present and in what proportions, and how that was changing over time. So they were able to look at the fitness of new variants, vaccine effectiveness, symptom profile, all these different things. And importantly, in the modern era, equity measures, because it was possible to compare across groups to understand whether what the origins of the disparities seen also in the UK were, and to what extent they were disparities in risk of infection, risk of bad outcome given infection, and so forth, so that interventions could be focused on the areas where the real problem was. This was a really remarkable set of work that was decided on and executed over the first couple of years of the pandemic. It has been largely dismantled since then, but I think it really shows what you can do with a very careful random sample. And I would also add that many people, I think, looked at that and thought that it was the National Health Service that made it all possible. The fact that there's a single insurer for the whole country, and that the and the records are centralized. My impression from a lot of conversations with the investigators in these studies is that a quarter or a third of the value came from linking to NHS records, but that really much of it was just from the random sample itself, which would have been possible even in a more chaotic country such as some that I'm quite familiar with. Again, in the spirit of trying to find clever ways to use data that we can get when the system is not as good as it might be, I think this paper represents an interesting idea where routine hospital-based testing for people admitted for non-COVID conditions can give a sense of prevalence and of variance and all of that. And the authors of this paper make an argument, which I think is interesting. I'm not sure if it's compelling, that after suitable reweighting, it's actually a more representative sample even than the surveys in the UK. So in summary of this little section, I think that we should think of different parts of surveillance as having different needs. In the pharmaceutical or vaccine world, there's the notion of a target product profile, that one designs a vaccine that needs to have certain characteristics, and the success of the design is evaluated against that product profile. And I think in a similar way, we should think about what is it we need in our systems for surveillance for different purposes, and then optimize them against those. And I won't belabor this long table, but this was a first attempt to try to create such a table. If you had asked me before COVID-19 what was the province of research and what was the province of surveillance, I would have divided it into the left-hand side as being something where you do a research study and then you have your answer and you use it throughout the whole event. And on the right would have been the things that we have to keep measuring over and over because they're obviously changing every day. In the COVID event, in the COVID pandemic, I think we've learned that because the virus sequence is changing and because vaccine effectiveness down below is changing, all these other things are also changing. And so severity is not a research topic, it's a surveillance topic, it's a repeated measure problem. Viral load kinetics may be different in different times in the epidemic. Transmissibility is surely different at different times in the epidemic. Natural history may be different, and sequelae. And so I would argue that in a way, this is a semantic distinction, that calling it research or calling it surveillance is maybe just a different word. But when we set up systems to do research, we really set them up to be optimized for one-time use and then a publication and then moving on. Whereas surveillance systems are designed and engineered to be able to go into practice over and over again, or even continuously. And I think for many of these topics, we need to move from a notion of individual groups doing research and telling us the answer to a notion that these are governmental responsibilities and that they need to be systems that can be deployed over and over again. And to do that, I think I want to turn to the second half of this talk, which is the value of integrated health systems in trying to do some of these things. So, yeah, I think these conclusions are pretty much what I've said, and I'll just reemphasize the last one, that COVID has expanded the remit of surveillance to include activities to monitor quantities that are changing over time, which used to be called research. And then part two, I'll explore that. So here I want to talk about integrated health systems and their potential role in pandemic surveillance based on experiences that I've had through the COVID pandemic in collaborating with them. There are many other examples as well. So these are just some of the ones that I've had the opportunity to work on, but I think they have some general lessons. Integrated health systems, particularly those that keep their people in them for long periods of time, can provide long-term longitudinal data on individuals. And this provides a lot of advantages in terms of matching of cohorts for prospective studies, analysis of subgroups, because you have large numbers of people in each subgroup and you know who they are. Depending on the accounting and data systems, there is often the ability to follow up individuals from transition from outpatient to inpatient. Ideally, there is automated merging of vaccine data with outcomes. And I think many ministries of health and state and provincial health departments have had to make strong assumptions about sort of, you know how many people are vaccinated and you know your population, and therefore you have a denominator of unvaccinated people, for example. That's troublesome for many reasons, including the fact that the denominator can sometimes turn negative if your records are not completely up to date or contain errors. And we've had issues of trying to interpret negative denominators. So when you're trying to understand what happens to people, it's much preferable to track the individuals than to simply count them. So I want to just now describe some examples of how this has been possible through 3 different sets of collaborations. The first one with the Clalit Research Institute in Israel, led by Ron Balitzer, Noah Dagan, and Noam Barda. And this is the research institute linked to the largest HMO or insurer in Israel. They've been digital for around 2 decades now. And Israel's system is that everyone must be a member of one of the 4 sick funds, as they're called, or health maintenance organizations. People tend to spend their whole life with one of those. They are allowed to switch, but it's unusual to switch, certainly to switch in any given year. And so typically people have a long period of data in a single HMO's database. This made it possible to, for example, do some of the things that I described, like look at large populations, in this case, an effectiveness study for the first 2 doses of Pfizer vaccine over about a 6-week period post-vaccination, studying 600,000 or so people in each group, the vaccinated and unvaccinated, in a very careful matching way that I'll describe in a minute. And then to look not only at the common outcomes that were studied in the randomized trial, but also at the unusual outcomes such as hospitalization and severe disease and even death that were not possible to study in this much smaller randomized trial of tens of thousands of individuals. So the approach of this was to do a matched cohort design, emulating a randomized trial, where the matching was intended to reduce other differences between the vaccinated and unvaccinated individuals that could confound the effect of vaccination. And so we matched individuals on age, sex, social sector, and so forth, history of flu vaccine, number of coexisting conditions. So this was a way of really trying to find very, very similar people, both geographically and demographically, and in terms of their health behavior, that would be as similar as possible in all ways other than vaccine. We were also able to use and check this matching and how good it was using what's called a negative control outcome. A negative control outcome is an outcome that you expect will be identical or nearly identical between the two groups, because whatever you've done, whatever the intervention is, in this case vaccine, should not affect that outcome. And from the randomized trial, we knew that there was no protection during the first 12 days after the first dose. And so if you can verify that that's the case in your study population, it reduces your concern that that differences that you do observe might be due to confounding, and makes you more confident in the causal interpretation of the of any difference. And we recycled individuals who were unvaccinated. When they became vaccinated, they entered the vaccinated population and found a new match to an unvaccinated person. This allowed also to look in subgroups, which was again not possible in the same detail in the smaller randomized trial that had been performed. So it was possible to estimate vaccine effectiveness in older people and in individuals with 2 or 3 coexisting conditions, and verify that it was at least similar, maybe slightly lower in the case of 3 coexisting conditions. This is the charts that helped us to trust the findings, in the sense that when we did our full matching and compared the vaccinated and unvaccinated people in the first 12 days, there was virtually no difference, certainly no difference compared to the scale on which differences appeared later on. And just for comparison, when we matched only on age and sex, which would be possible in a larger database with less detail on more people, we began to see more divergence between the two, suggesting that confounding was not completely controlled by that kind of matching. It was also then possible to look at vaccine safety and the sequelae of infection. We performed a second study which looked at 2 exposures, either vaccination or documented infection, and then asked what outcomes individuals had, which was a safety study in the case of the vaccine exposure, and a natural history study in this case of the documented infection study. And so comparing individuals with and without vaccination, in the bluish gray color, we saw slight elevations in a few outcomes, but very modest, except for lymphadenopathy, which we expected to see as a result of vaccination, and then substantial risk differences in the number of individuals who following infection experienced bad outcomes. And helpful, although these are not precisely comparable cohorts because they were different groups of people, it is helpful to see the sort of magnitudes of some of the concerns that people have had, such as myocarditis, which was about 11 per 100,000 in people who had been infected and documented, whereas it was about 3 per 100,000 in people who had been vaccinated. And then using the household data from this same HMO, it was possible to look at the protective effect of parental vaccination on children, because you could include people who were in the same household who had the same insurance. And so you could see a 95% or 94% direct effect that the parents were less likely to be infected if they were vaccinated, at a time when the children were not yet eligible because it hadn't been rolled out to them. Children in vaccinated homes were 72% less likely to get infected if their parents were infected. So it was a transmissibility effect, presumably. And then overall, one vaccinated parent reduced a child's risk of infection by about 26%, and two vaccinated parents by about 72%. And then working with them, it was possible to look at third doses and fourth doses and a number of other topics over the course of multiple variants and so forth. The last thing I want to say actually about these vaccine studies is that there is some segment of the scientific community that sort of argues that without randomized trial evidence, we shouldn't make clinical decisions. These were all observational studies, not randomized, done as carefully as possible to estimate causal effects, but with all the concerns that an observational study has. It's worth mentioning, however, that it was not possible to do randomized studies of almost any clinically relevant topic by the time that would be informative about effectiveness by the time those questions became important. It was not possible to estimate effect against new variants because people had already been vaccinated, and so it was too late to have a control group, a randomized control group. It was not possible to look at waning of effectiveness because, again, the vaccination had already happened at a population scale. It was possible to do booster studies, but only on a small scale, and certainly not in the context of all the variants that were circulating by the time it was relevant. So the fact that events happen quickly means that observational studies become more and more a part of what we have to use to make clinical decisions. I think I might, in order to have more time, I might skip the part about sequelae, just because I want to have lots of time for discussion. But we did a couple of studies with United Health in a similar database, but more based on claims rather than on electronic health records, so insurance claims. And we're able to compare individuals who had COVID-19 to individuals with other viral infections, shown in the blue. The purple is COVID, and the blue is other viral infections, and the other two colors are the individuals who did not have documented COVID or any other infection. And you can see sometimes COVID acts kind of as a like a typical viral infection in terms of the risk of cardiomyopathy after infection, and in other ways it acts worse than another viral infection. For example, this outcome. And then we did it again in Medicare. But the last example, and this should be number 3, misnumbered here, but the last example was work that I got involved in my CDC capacity, which was to look at Omicron severity with the insurer and provider Kaiser Permanente of Southern California. And the setting for that was that it was clear in late November of 2021 that Omicron was coming. We could see that from South Africa. It was not clear, and it was also clear that it would cause a lot of infections because of its immune escape properties. What was less clear is how severe those infections would be compared to the Delta wave that had just hit. So we set out in the Center for Forecasting and Outbreak Analytics to see if we could obtain data on this question. Contacted a colleague, Joe Lunard, at the University of California, Berkeley, and rapidly designed an analysis with collaborators at Kaiser Southern California, which, as I mentioned, is a large integrated health system. Many pieces of good luck happened in terms of the timing and the quality of the investigators involved and the timeliness of their data. And with all of that good luck, it was possible to obtain estimates within a month of starting the conversation. And the CDC director presented the first results, and a preprint was submitted within 5.5 weeks or so. So this was largely done not only to understand Omicron, but to see what the sort of proof of concept might be for a faster approach to answering these questions than has been done in the US in the past. So the approach with this was that individuals were diagnosed in a way that could identify the genetic marker, the S gene target failure that was characteristic of the BA.1 original Omicron variant. So one of the pieces of good luck was that the colleagues in Southern California largely used a device for PCR that could identify this phenotype. So it did not depend on sequencing. And when I said that COVID-19 has been teasing us, one of the ways in which it's been teasing us is by alternating frequently between variants with this S gene target failure and S gene target success or positivity. And so it's been repeatedly possible to distinguish the two most common variants in circulation, as it is once again with XBB, by their S gene target phenotype. So initially we analyzed S gene target failure, which was Omicron original versus Delta, and then later on as BA.2 flavor of Omicron swept through, it was possible to compare that to original BA.1. And these were the results. This was, again, with individuals who were infected, who were diagnosed in the outpatient setting, and then were followed through their clinical course, possibly to inpatient setting. So this looks at the risk of hospitalization, which was about 1/3% for Omicron and about 1%, a little more than 1% for Delta, with a hazard ratio of about 0.6. Similarly, for admission with symptoms, intensive care unit admission was 50% lower in individuals with Omicron than Delta. Mechanical ventilation was 2/3 lower, and mortality was 80% lower. So still severe, but much milder than the Delta variant that had preceded it. And then in comparing BA.1 to BA.2, these differences were not apparent, and they were completely overlapping. Oops. We could also look at length of hospital stay, which is important for resource utilization, and it was considerably shorter in BA.1. So in closing, I said that there was a lot of good luck involved in this collaboration. The presence of BA.1 early on in Southern California was important. Having a payer provider with a deep electronic health record and linkage to the state vaccine registry so that vaccination could be included in our analysis. Really excellent analysts, both at Kaiser and at UC Berkeley. There was good luck in that their machine was one that could see S gene target failure, and in the fact that S gene target failure could distinguish BA.1 from Delta. And important in government land is that there was already a CDC contract with this group at Kaiser to build on, which allowed us to move quickly. So this is not how we want to do things in the future. We would really like to have the ability to do this this kind of work with regularity and with higher certainty that does not depend on as much good luck. And that's really been a lot of my role at CDC, is trying to build the systems to do that. And we're partway there. We're certainly not done. I think an aspect of that that has really been outside the UK has really been lagging is the notion that we need to include pathogen genome data as part of our epidemiologic line lists. In 2014, Jonathan Grad and I, apologies for my dog, Jonathan Grad and I suggested that the sequence should be the last column of a line list for epidemiologists, which seemed like a fairly common sense suggestion at that time. It is still far from typical outside, again, the UK and a few other places perhaps. But it is so important in a pandemic setting because without knowing what strain you're dealing with, you don't know much about what your data tell you. There are periods when you know because there's only one strain circulating, but there are periods when you really don't, and those are the periods of greatest need for data. So to finish up, I think the use of these kinds of integrated health systems or payer providers especially can provide close to real-time evidence on almost all the things we want to know. And they have the ability to emulate randomized trials in observational data, including for subgroups and scale, so that we can look at rare outcomes. As I said before, we need to move from seeing these as one-time splashy articles to a more surveillance approach that is much more something we're constantly updating and reporting on a weekly or monthly basis. And I think, again, the UK is probably the leader in this. And for using these data sets, I think their high quality can outweigh their moderate size and imperfect representativeness for many questions. These integrated health systems are not the best way, I would say, to monitor the burden of disease and the number of people infected, but they may be very good ways to answer more difficult or more detailed questions about severity and countermeasures. And again, the need to link to fast sequencing. So I'll stop there, acknowledge some other colleagues who have been really helpful in thinking about these questions, and I'll leave some time for discussion.
Thank you, Mark, for this outstanding talk. Do you have any question? Oh, yeah, Nicola.
Thanks. I have, first of all, thanks, Marc, for the excellent talk about COVID-19 epidemiology and the challenges of epidemiology in our contemporary society. I am a medical doctor and an epidemiologist, and I would like to ask you this question. In a very famous article published in Nature Communications, Griffith and co-authors have warned about the risk of collider bias and other biases that can affect studies. They have stated that COVID-19 has seen a proliferation of observational studies, most of which don't use random sampling and have usually had conflicting results. And they say our epidemiological understanding of COVID-19 is seriously affected by several biases. So my question is, what do you think of this finding by this study? To which extent do you believe our current epidemiological understanding of COVID-19 is affected by biases? And of course, biases can occur in epidemiology, but in particular situations like a pandemic, in which time really matters. How is it possible to avoid biases?
Thanks for the question. I don't know the paper you're referring to, and I'd love to read it because I think I probably quite agree with it. So if you could email me the citation, I would really appreciate it. I think it's true, and for those who are not in this particular jargon, collider bias is also sometimes known as selection bias, and is the consequence of conditioning one's sample on the common effect of two causes, which therefore induces a correlation between those causes, even when it is not present in the source population. An example might be conditioning on looking at hospitalized individuals and the probability of progression given vaccination, the probability that one gets hospitalized, given that one has been infected and was vaccinated, what is your probability of, how does the vaccine affect your probability of progressing to hospitalization? And this, because the individuals who have been infected are not a representative sample of those in the population who were vaccinated, there can be a bias in this analysis. I'm not explaining it well in real time, I apologize, but this is a recognized issue. I think it is quite common, and certain groups seem to do it repeatedly, and other groups seem to be more cautious about it. One way to avoid it is to start from the moment of infection, and we're actually working on a paper about ways to avoid this, but it's really hard because you often don't observe the moment of infection. Sorry, to start from the moment of exposure, because you often don't observe exposure. Another way is to compare two different groups with similar exposures, and that was the approach that we took with the Israeli data. So I think it's an important question. I would love to read the article, and I think it's a long discussion about what methodological approaches can best solve this, but it requires training and causal inference to even recognize the problem. And I think one of our jobs as epidemiologists is to improve the understanding of these ideas in the community as a whole, including the researchers.
John Hong, you can ask your question.
Oh, thank you, Mark. Thank you for coming to the fields and to him for public health event. And I'm Jianhan Wu from York University. I'm a moderator. Mark, I have a question that's about the population behavior data and surveillance. I know this is controversial for epidemiology and for CDC surveillance system, but it is fundamentally important. And how do you think from the epidemiological and from CDC point of view, how to approach this?
I'm not sure I understand the question.
I'm talking about the behavior data and hesitance, and those are relevant to culture, to communication, and miscommunication, and this is out of a traditional medical consideration, and how the government, how CDC, for example, want to watch on this data and collect this data and analyze this data.
By behavioral data, you mean, I'm not, there are a lot of different kinds. I'm sorry. I'm not,
yes, I'm talking about, for example, the adherence to different public health interventions, the vaccine hesitancy, and so forth.
Well, I think this is an area where and I'm speaking again in my private capacity, I think this is an area where governments need to get a lot better at understanding through surveys and through other means what people's preferences are and how to reach them. I think that in the first year of vaccine availability, there were some efforts to understand reasons for not getting vaccinated and to counteract those. I think there's room for getting much better at that, but it's certainly not my area of expertise.
Thank you, Mark.
Other questions?
Hi, my name is Dongmei Chen. I'm from Queen's University. Thank you very much for this presentation. Actually, this provide a very good different perspective to using those kind of research data in the surveillance systems. One question I have is many of those kind of the small scaled or large scaled research data, for example, like how effective of vaccinations. There are, in some ways, it's kind of the delayed. Usually it's kind of the after, like outbreak that already happened there. So although they are very accurate, but they are not kind of, matching with, actually where like we expected for the surveillance systems, which is usually before outbreak. Before anything come out, we can predict what will be happening, right? So how are going to using those like in the surveillance systems to predict or give us the warning signs or help us prepare the world of the health resources? So what kind of like your insight on that?
Yeah, I think that there's a lot of discussion about trying to predict what the next pandemic will be or what the various threats are. And I haven't seen the evidence that we actually have the ability to do that. I mean, in some vague ways, people have had their eyes on coronaviruses because there have been SARS-1 and MERS that warned us. And even before that, Don Burke pointed to coronaviruses as one of the families that we needed to pay attention to. But other than these broad potential areas of threat, I haven't seen the evidence that we know how to predict. I think detecting early and preparing across preparing means that are of response that are generally useful, such as new technologies for developing vaccines and diagnostics, is the state of the art right now. I think it's certainly possible that prediction will become easier, but for any very rare event, meaning there have only been a handful of world-class, world-shaking pandemics of anything in the last 100 years. And I think we have to be humble about saying we're going to know what's coming before it comes. But we, on the other hand, can prepare for a broad range of possibilities with general purpose approaches and then specific approaches to the broad categories of viruses that we think are of highest probability. And I think just based on recent years, that has to include influenza and coronaviruses, but you could then discuss which other categories. So I understand why people want to predict the future. We all do, but I think in the next decade, what we need to do is put some investment in research into how to do that, but really focus on preparing for the broad categories of things that we think are likely, so that when we do detect something, we have a head start.
Thank you. Any other question? Any question from the people on Zoom? No? So thank you so much for your talk. It's great to have you today here.
Thank you for the
So-
invitation. Sorry to miss people in person.